Okay, so good morning and happy Friday to everyone. Today we're going to talk about the operational method for solving systems of differential equations, linear systems. And again, what we're going to do today falls under that general description that I gave you, where in order to solve differential equations, we come up with all sorts of interesting and new methods that do not necessarily resemble things that you had seen in the past. And you're going to see that this is going to be quite the case today with what we're going to discuss. And let's begin with a little bit of motivation, how the kind of problems that we're going to look at would arise in application. So let me remind you that we had seen the problem of compartmental analysis, right? And you had a tank that had a brine solution that had a certain amount of salt. And then you could have initiated the inflow of fresh water, or again, a brine solution with a possibly different concentration of salt. And you wanted to study the concentration of salt in the tank with respect to time. And please understand that, and this goes for many of the things that we have seen so far, that the last thing we possibly care about in this description is a water tank that contains salt. What do I mean by that? We have an instance of mathematical modeling here, where we take a specific problem and we find a concrete situation to which this problem is applies, and we give the description of that concrete situation in order to introduce the mathematical concept behind it. But what one should not forget is that that specific mathematical description is not necessarily our destination, what we want to study. In other words, it is possible to arrive at the same mathematical problem from a completely different actual situation. And this is what mathematical modeling is all about. And here, the general idea is that you have mixing problems. So for example, maybe you don't have a tank of water. Maybe what you have is a country, and it has a certain amount of people with a certain characteristic. And then there is an inflow of people and an outflow of people. And you try to understand how the concentration of people that have that characteristic changes. Or we could be talking about a certain species in an ecosystem. And again, you have an inflow of so we can talk about a full population that involves different species, and then we have the infusion of a certain species in that population, and you want to see how much its numbers changes through time. So what I'm saying here is that you can have a lot of very, very interesting and very, very diverse situations to which what we're saying applies. And that's why when we talk about tanks of water here, you should not just be saying that, oh, okay, so what we're studying here is very narrow in scope, and I don't care about something like that, because it's very possible that actually some problem that you do care about is has to do with something like that. Now, what I would like to do today is begin our discussion with two tanks. Okay, so again here, I would invite you to use your imagination as to how or what other kinds of situations a description of this type could include. And let's write some numbers down. Okay, so let's say that this tank has 100 liters of brine solution, and this one has 200 liters. And here the initial amount of salt, the initial mass of salt, if you will, is 1 kilogram. And here it's 1.5 kilograms. And here what you have is an inflow this way, and then you have two flows that go in the two different directions. So you have one that exits, let's say, the tank A and goes into tank B, and one that exits the tank B and goes into tank A. And then you have one more flow that goes out of tank B. Okay, so look at this picture here, and I would like to give you some numbers here. So let's say that this inflow is 3 liters per second, per minute, of fresh water. So this is fresh water, no salt in it. The height, I'm not sure what you mean by the height here.
You just make the input such as more higher than the output. Is this a matter or no matter here?
All I have given you here is just the inflow. I haven't given you any other number yet. I have given you the volume in tank A and the volume in tank B, and they're both, I mean, they're different. They don't have to be the same. And yeah, that's all. And here you could have, let's say, to get this started, we could have a 5 liters the outflow, which means that you're losing 2. So let's make this 2 liters. And for B, you gain 3. So let's make this 3. Again, if per minute. And you can see that the way that I gave you the numbers, the volume in both tanks remains constant. Okay, now do I have to make it like this? No, it doesn't mean that it has to be constant, but actually it's a good idea to keep it like this. Okay, it's going to simplify things for us, because now we know that the volume in each of the tanks remains the same. Okay, so far so good. Does everybody understand the problem? And of course, here we said x of t is the amount. When I say amount, I really mean mass of salt in tank A. And y of t is the amount of salt in tank B. And what we would like to find is we would like to find x of t and y of t. That's the problem. Okay, so pretty much we're looking for two functions that tell us how x and y change through time. Okay. Any questions on the setup? So let's try to solve this problem. So as usual, we try to find information regarding the rate of change of x in and y in the two times. So I would like to start by writing dx over dt and ask myself what, and ask you actually, what contributes to the rate of change of the salt in tank A. So first of all, the inflow, this inflow from A doesn't have any bearing in on the mass of salt in the tank, right? I hope we can all agree on that. And as for, so what really matters is the two flows between A and B, right? So first of all, we have an outflow from A to B. And how's that going to affect the situation? The concentration. So it's going to be a minus 5 liters per minute times the concentration of salt into in tank A. And what is the concentration of salt in tank A? X over 100, right? X over 100. No, I'm talking about the concentration, not the amount of salt. The amount of salt is 1 kilogram at time 0. But when you write the differential equation down, you don't want to just take into consideration what happens at time 0. You really want to take into consideration what happens at any point in time, right? And then there is a positive contribution to the amount of salt in tank A from the inflow, coming from the inflow, from the flow from B to A, which is 2 liters per minute. And this corresponds to a concentration of Y over 200, okay? Now, can I ask you to try to write a similar equation for dy over dt? Would you like to give it a try? Now you have to be careful here because this time around you will have 3 contributions, right? I mean, you have the outflow from B and the 2 flows between A and B. Okay, so there will be 3 of them, but you can really combine them in 2 of them because 2 of them depend on the volume of on the concentration in tank B. Just give it a try and then we'll do it together. Okay, let's see together now. So let's look at what depends on the concentration in tank A. So that contribution is positive, right? And you have 5 times x over 100, right? So I'm talking about this contribution right here. Okay, and then you have 5 liters all together that they exit as a total. You have 2 directions, so you have this direction and this direction where those 2 outflows, and this have to do with the concentration in B, so, or with the tank B. So here you will have minus 5 liters per minute altogether times y over 200, and that's our system. Okay. Any questions, please?
Yeah, how come it's -5 times y over 200 here, but we didn't do that for the one above it?
Because for the one above it, first of all, we did do something similar. It's right here. And the situation for the 2 tanks is not symmetric. In other words, what happens in one tank is not exactly the same as what happens in the other tank. Meaning in tank A, you have an inflow of fresh water. You don't have any such inflow in tank B. And also in tank B, you have an outflow of brine solution, which is not what you have in tank A. Okay, so
But technically, wouldn't you say that there is an outflow solution because it's going from tank A to tank B?
Yeah, and we accounted for it right here for dx over dt. This is where it's accounted for.
So, like, what happens to the fresh water? Like, where did the fresh water go in tank A?
Please note that what you're actually analyzing is the amount of salt. The fresh water doesn't have any salt in it. So it doesn't introduce any new mass of salt in tank A. That's why it's not taken into consideration when we find the dependence of the salt in tank A.
Oh, okay, that's what I was confused about. Okay, thank you.
And if you look at the one tank compartmental analysis that we did way back when, you will realize that we had a similar situation. I think back then we had done a small variation on this theme by considering the situation where the inflow has a certain concentration of salt. But the truth is that, we can, here we just disregard it because it's just fresh water which is being introduced. Okay. Any more questions? Okay. So another question, so what we get is a system of differential equations. And please understand that in actual applications, in most applications, you will have systems of differential equations rather than individual differential equations. That is what is usually going to be the case. Okay, why? Because you have more than one parameters that somehow affect the system under consideration that you will have in front of you. So what we would like to do is not try to solve this as some isolated problem, but try to come up with a strategy, a very, very interesting strategy that actually can work for several of these cases. So, so here's the new thing that we're going to add to this situation. So what we will start doing today is think of dx over dt as don't even want to write an equation. Think of this as multiplication by an operator D. So we would write this as D times X. So D times X for us is taking the derivative. And in general, an operator doesn't need to be, I mean, the term multiplication here is rather formal. It doesn't mean an actual multiplication. It just means that you operate on X in a way that changes that X, and you just use a notation that might refer you to actual multiplication. There's no multiplication that takes place here. It's just a notation that might actually have you think that you're dealing with multiplication. It's not really a multiplication. So if you do this, then the system on the top can be written as dx is equal to minus 0.05 x plus 0.01 y, and then you have dy is equal to 0.05x minus how much is this going to be? Minus 0.025y, right? That's what it looks like. And then here comes the novelty. Here comes the new approach, if you will. You bring everything to the left-hand side, and you bring 0.05 and d together, and you think of their sum, their formal sum, as multiplying x minus 0.1y and d plus actually, let me write x here first. So this will be minus 0.05x plus d plus 0.025y. The y, the whole thing applies to y. And in both cases, since we collected everything on the left-hand side, we're going to get 0 on the right-hand side. Okay. And that's what we get. And in some sense, this resembles a usual linear system of equations. The only difference that you have here is what you're multiplying is not just numbers. It's these formal symbols. So one of the things that people try to understand in the transition from the classical mathematics to the more modern mathematics is what is exactly the mechanism that underlies this kind of situation. And the truth is that we're not going to go deep into that mechanism. But pretty much what we have here is what we call in mathematics rings. Okay, so it turns out that if we take the things that look like d plus constants, those things can be thought of as belonging to a mathematical structure, an abstract mathematical structure, which is called a ring. And in a ring, we can do two things. We can multiply things together, and we can add things. And there is, or the elements of the ring, and there are some very natural properties that we expect to be fulfilled in those cases. Okay, so that's the idea behind rings. And in particular, what one is considering here is a ring of operators. So it's a ring of objects that operate on functions. And how do they operate on functions? Well, every time you apply d to a function, you just take its derivative. Every time you apply a number to a function, you just multiply the function by that number. So pretty much the status of those operations is a given in some sense, and you can use it in order to find what is happening with as those objects act on those functions. Questions, please.
When you say constant, you mean that is the 0.05 is a constant here? Any
Yeah.
number will be
Yeah.
added today will be constant? Thank you.
Well, we have a particular situation, and yes, we have a constant number. And what we're interested in is the way that that number acts on functions. And the way that this number acts on a function is just it multiplies the whole function by that. There's multiplication of the whole function by that number. There was also a question asking if this whole thing is related to groups. And the answer is yes, it's absolutely related to groups. But we have a structure which in some sense is much richer than that of a group. So what we have is actually an additive group that has an additional multiplication to it that enjoys certain nice properties. Okay, so if you look at abstract algebra, which is something that I don't wish to do today, then you will realize that there can be a very systematic study of these objects using the theory of groups and rings. And the theory of groups and rings is a mathematical theory that was developed in the 19th century, but you can understand that it found its modern form in the 20th century, and it took a little bit of time before people were actually used to this. Because here's what I want you to understand, and we're going to see how we're going to do this, that at the end of the day, we're going to pretty much think of those objects in front of X and Y as numbers, Now, are they really numbers? No, they're not. But the truth is that by considering them as numbers, we will be able to do a study very, very similar to or we will be able to handle systems in this system in a way very similar to how you handle a system of equations, of regular equations. So in other words, you're going to see that we're going to apply a sort of elimination method to that system. So this system, because of the decimals, may be a little uncomfortable to solve. So I would like to give you a very, very similar system that we're going to solve in a much more, a much smoother way. So let's consider the following system. First of all, actually, before I give you the system, I should say what is the most general form of systems that we can solve this way. And pretty much what is going to happen is you can have a system that looks like this. So you can have, in what we're going to do today, you could have something like A1D plus b1 times the function x plus c1d plus d1 times y is equal to a function g1. So g1 is a function, and a2 d plus b2 x plus c1 c2 d plus d2 y is equal to g2. So here a1 b1 c1 d1 a2 b2 c2 d2 are real numbers, and g1 and g2 are functions of t. If you look at the system that we had in the previous page, you will realize that g1 and g2 were 0. And in this case, the system is called homogeneous. And but the case that we're covering here doesn't have to be that of a homogeneous system. It's just that we're going to have a little bit, a slightly larger amount of work if the system is not homogeneous. So you will see that for most applications that we're going to have here, we're going to look at homogeneous systems. And I would like to show you completely how to solve such a system. So let's take something like x prime is equal to 4y minus 3x, and y prime is equal to 4x minus 3y. Okay, so let's consider this system. Again, you can see that the system is given in exactly the same way that we obtained the system of equations in the two-tank problem that we just saw, but we're going to transform it and in the way that we wrote the system in the previous example. So in other words, what I would like to do is I would like to rewrite this as dx is equal to 4y minus 3x, and dy is equal to 4x minus 3y. And then I would like to rewrite this as d plus 3 times x minus 4y is equal to 0, and 4x plus d plus 3, actually minus 4x plus d plus 3y is equal to 0. Okay, so now it's written in a more classical way. Any questions, please? Okay, so now we would like to solve this system. And how do we solve such a system? The idea is pretty simple. First of all, when you have a system, you can actually add the equations together. Why we switched? We didn't switch it. We just brought it over to the other side, right? So it was on the right. When you bring it on the left, you have to change its sign, right? Okay. So the idea is as follows, that you will have to create pretty much opposite coefficients for x. And when you have created opposite coefficients for x, then you will be able to add the two equations and get rid of x. And then you will have a differential equation that has only y. Okay. And that should be enough. That should help you to actually solve it. So So what I'm going to say here is that I'm going to multiply this by 4. And I'm going to multiply this by d plus 3. Look at the description that we gave before, and maybe I should have said what x and y are. So x and y are functions of t. In some sense, what we're going to do is happening in 2 stages. In the first stage, you try to isolate either x or y. So you try to come up with an equation that has just x or just y. That equation that you get, though, is not really an algebraic equation because d is differentiation. So guess what? You will have to actually treat it as a differential equation, and you solve it as a differential equation. And once you find x, you plug it into one of the 2 equations. Actually, that part is a little quite interesting to do carefully, and you get y. Okay, so what you really want to find here is 2 functions of t. So x and y are functions of t. Okay. So if I multiply the first equation by 4, what do I get? I get 4d plus 12 times x minus 16y is equal to 0. And if I multiply the second equation by d plus 3, what do I get? I get minus 4d minus 12 times x plus d plus 3 squared y is equal to 0. Now, this needs a little bit of discussion. So we need to discuss this a little and understand what is going on. So what do I mean when I say d plus 3 squared y? This is where that concept that I briefly discussed before kicks in. So when you work with expressions that involve d, you can actually multiply them together. So this thing is going to be d squared plus 6d plus 9. That's our usual identity, right? The question is, what is its action on d, on y? What does it mean to act on y? And when you multiply by d squared, can anybody guess what the effect on y is going to be when you multiply by d squared? So d means to take the derivative, right? So what does d squared mean exactly? So d squared will be to take the second derivative, and 6d will mean 6 times the derivative of y, and then plus 9y. Okay, I know the first time that anybody ever sees something like that, it looks very strange. Okay, it looks very, very strange. But it's actually, in 20th century mathematics, this is actually a quite routine thing to do. Any questions? Okay, why don't we take a break and let this sink in for a second, and we're going to continue and see how we're going to complete the solution of the system. Okay, let's solve our equation now. Does anybody have any solutions? I'm sorry, any questions, not solutions. If you have solutions, that's even better, but I'm pretty much looking for questions. Okay, then. So what I'm going to do is simply what I showed you. So I'm going to add the two equations together. And when I do so, what is going to happen, this is going to cancel with that. And what you're going to get is d plus 3 squared minus 16, y in both cases, is equal to 0, which of course can be interpreted as I told you before, as y double prime plus 6y prime plus 9y minus 16y is equal to 0. And that eventually gives you y double prime plus 6y prime minus 7y is equal to 0. Okay, and now you have an equation that should appear to be quite usual. So what you do is you're going to solve it as a second order differential equation with constant coefficients. So it's going to be the corresponding auxiliary equation or characteristic equation is r squared plus 6r minus 7 is equal to 0, which means that delta is going to be equal to 36 minus 4 minus plus 4 times 7, which is 28 plus 36, which is 64, right? A very nice square discriminant. And the solutions are going to be minus 6 plus or minus square root of 64, also known as 8, divided by 2. And this is going to give you minus 6 plus 8 is 2 over 2, that's 1. And minus 6 minus 8, that's minus 14, divided by 2, that's negative 7. Right? So these are the two solutions, which means that y1, y of t, is going to be equal to c1 e to the t plus c2 e to the 7 e to the negative 7t. Okay. So far, so good. Are there any questions? Okay, now I want you to understand that up to this point, the process is pretty much the same and quite straightforward. And I don't think it has any particular difficulty because you will apply your elimination method. So first of all, you will represent it as in operator form. Then you will apply your elimination method. And eventually you're going to obtain one differential equation. It could be homogeneous, it could be non-homogeneous. You're going to solve it no matter what. You're going to find the general solution. The question that comes up now is, once you find y, how do you find x? And here there are different things that you can do. Okay, one thing that you can do here is actually you could apply pretty much the same principle So you could go back to this system and this system right here, and try to apply elimination so that you get rid of y. And you would do exactly the same thing. So you would multiply this equation by d plus 3. You would multiply this by the second one by 4. And then when you add them up, the y's would cancel each other. And it would appear that this is this would give you, first of all, an equation that would have the same auxiliary equation as the one that you had for y. And when you solve it, here comes the tricky part. Okay, here comes the tricky part. When you solve it, you cannot put C1 and C2 as the constants. You have to somehow show that the constants can be chosen independently of each other. Meaning the constants for the y function should be chosen. I'm sorry. If you choose them independently, then you give yourself too much freedom. It would appear that you have 4 independent constants, and that's simply not true. That's simply not true because you have equations that involve both x and y, and those equations impose a certain dependence of the x's on the y's and vice versa, or on the constants of the one equation to the constants of the other equation. So eventually, the rule of thumb for these systems is that you should find 2 constants. Eventually, you should find 2 constants. So eventually, you should express everything by using 2 constants. Now, here comes the problem. Depending on the actual situation that you have, making that identification might be a little convoluted. Okay, not impossible. You will have to just plug the x and y into both equations and see what dependence you're getting from between the constants of the 2 solutions. What I'm going to suggest here is something which is much, much simpler. And the starting point for this is going to be the second equation. Do you see how the second equation really tells you what x is in terms of y prime and y? I mean, you will have that 4x is equal to y prime plus 3y, which means that x is equal to 1/4 y prime plus 3/4 y. Do you see this? That's what we're going to take advantage of. Okay, that's what we're going to take advantage of, and we're going to find x right away. So we're going to take this y and we're going to plug it in there. Okay, so allow me to change page and remind you that yt was c1 e to the t plus c2 e to the negative 7t, and x was equal to 1/4 y plus 3/4 y prime. Oops, was it this way or was it the other way? Let me see. The other way. Sorry about this. So the prime should go here. Okay, so now we're going to plug them in. We need to know what y prime is. So what is y prime? Y prime is going to be c1 e to the t minus 7 times c2 e to the negative 7t. Okay, and now we plug them in and we get 1/4 c1 e to the t minus 7 c2 e to the negative 7t plus 3/4 of c1 e to the t plus c2 e to the negative 7t. And, obviously we can bring things together and write this in a much nicer way. So we can write this as 1/4 C1 plus 3/4 C1, that's 1 C1, right? So that's C1 e to the t. And then you have minus 7/4 plus 3/4. That's minus 4/4, which is minus C2 e to the negative 7t. And now, so this is x of t. And now this is your solution. And it all depends on two constants. You can use the constants any way you like. Or you may have an initial value problem. Okay, it is possible that you actually have an initial value problem, in which case you can plug the values into the solution and determine C1 and C2. So for example, if you look at the very first problem that we have done, this could have been given as an initial value problem. What would have been the initial conditions here? The initial conditions would have been that x of 0, the mass of salt in the first tank is 1 at time 0, and y of 0 is equal to 1.5, and that's it. So if you had solved the system, as you saw, I avoided to solve the system in order to, solve a much simpler one, so that as to focus on the method rather than on the complications of the numerical complications that would ensue from a system of this type. But regardless, you would have solved it. You would have found C1 just two constants, and then you would have been able to determine those two constants on account of the initial conditions. Okay.
So I would like to ask why, can you go back to the previous page?
The one where I had the tank problem?
No, the one that's right before this one.
Okay, here we are.
Yeah, so why didn't you just solve for the it's solve for x of t the same way you solved for y of t from here?
Okay, so let me repeat what I said before regarding this. So first of all, I said that it could have been possible to start with this and apply the opposite kind of elimination that would eliminate y and get an equation in x. If I did so, you would have seen that it would have had the same auxiliary equation with y, and I would have needed to find, so in other words, what I'm saying is I would have got something like this. I would have got x double prime plus 6x prime minus 7x. And I would have needed to pretty much put a different set of constants. So k1, let's say, e to the t, plus k2, e to the negative 7t. Why? Because there's no particular reason why this C1 should be the same as that number and this number should be the same as that number, at least initially. The difficulty here is that if eventually I gave my solution to the problem this way for x and y, this would have been simply wrong. This would have assigned too much flexibility on the choice of C1, C2, K1, K2. It would have given you supposedly the false idea that you can choose four constants anywhere you like. Well, that's simply not correct. That's simply not correct because there is dependence. The x and y are in the same equations, and there is dependence of x and y in and the dependence in x and y brings dependence between the C1s and the K1s. Now, does that mean that the situation would have been pretty much impossible. No, you would have still needed to establish a dependence between the x's and the c's and the k's. The way that I chose to do this is simply much faster. It allows you to obtain the dependence between the constants in the expression for the function x and in the constants in the expression for y automatically. Okay, that's all I'm saying. So this thing here is simply not needed. The question is what I just did as general as it gets? And the answer is a very unfortunate no. A very unfortunate and resounding no. It's not that simple. Okay, so in most cases, it's not going to work smoothly like that. And when I say in most cases, in the case of the generic system of this type, it's simply not going to work this way. So there are some things that I would like to, so are there any more questions? Because I would like now to go to your homework and take a look at the problems on your homework, because there are some interesting things going on there. Yeah, sure. So are there any more questions, please? Okay, sorry about this. Let me mute everyone. Okay, so take a look at the homework now, because there are some interesting things that I would like you to see here. There are some very interesting variations on the kind of theme that we just looked at. And for the first one, I just want you to apply the elimination system, the elimination method, the method that we just showed. And but please do not attempt to solve the system. I would like to get you started with this problem, because there's something very interesting to it that you may miss if you look at it in a very general way. So this is the most general kind of system that you can have, right? So 2x prime plus x plus 3y prime plus y is equal to e to the t x prime plus 2x plus y prime plus 3y is equal to sine t. Okay, something along these lines. Your first order of business here is to write it in operator form. So you should write this as 2d plus 1 times x plus 3d plus 1 times y is equal to e to the t, and d plus 2 times x plus d plus 3 times y is equal to sine t. Okay, so this according to what we already said. Here comes the interesting part that I would like to show you. So so what would you want to do here in order to eliminate x? Let's say if you want to eliminate x, you should multiply, let's say, this equation by negative t minus 2, and this equation by 2d plus 1. Do you all see why this is true? Because if you multiply the first one by negative t minus 2, then the coefficient of x will be 2d plus 1 times negative d minus 2. If you multiply by the second one by 2d plus 1, so for the second one, the coefficient of x will be 2d plus 1 times d plus 2. So the two of them are opposite of each other. And pretty much they're going to cancel each other. Okay, so that's what is going to happen. They're going to cancel each other. However, let me show you how the first multiplication is going to happen. So let me actually do the first multiplication for you. So what is it going to look like? So you're going to have minus d minus 2 times 2d plus 1 x plus minus d minus 2 3d plus 1 y is equal to minus d minus 2 times e to the t. Okay, that's what you're getting. And this is the point that I wanted to make. What is exactly minus d minus 2 e to the t? You need to do a distributive law as usual. So you need to multiply e to the t by negative d, and you also need to multiply it by negative 2, right? So now the question is, what do you get if you multiply e to the t by negative d? And the answer is, so what is minus d times e to the t? It's minus the derivative of e to the t. And the derivative of e to the t is minus e to the t. And what do you get when you multiply minus 2 by e to the t? And the answer is minus 2 e to the t. So the whole thing is going to be minus 3 e to the t. That's a very unusual thing compared to what you have seen so far in cases like this. Okay. And let me also do the other multiplication, 2d plus 1 times sine of t. What do you get here? So it's going to be 2d times sine t plus 1 times sine t. Okay, 1 times sine t is sine t. What is 2d times sine t? Can anybody tell me what is 2d times sine t? Exactly, but with 2, right? Let's not forget the 2. So it's 2 cosine t plus sine t. Okay, that's what it is. Okay, that's where I want you to be careful. And please do not solve the resulting equations. Now, on the first problem, all I want you to do is carry out the elimination method. It's going to be pretty unpleasant if you actually try to solve for the resulting equation. Okay? Any questions, please? Let's take our attendance. I want you to tell me what is d cosine of 3t. What is d times cosine of 3t? Okay, that's for the attendance. Okay, I'm getting some correct answers now. I'm getting very many wrong answers. All you need to do is tell me what the derivative of cosine of 3t is, right? Don't forget your chain rule. It's minus 3 sine of 3t, right? Minus 3 sine of 3t. Okay, are there any questions, please? Are there any questions? Okay, then. So I wish you a very, very nice weekend, and we'll talk again on Monday. Okay?